Greetings to the respected faculty. I am Lasya Mandapati from CSE AI&ML B section. My roll number is 24951A6686. And today we'll be exploring one of the most fundamental yet fascinating aspects of computer architecture. That is arithmetic microoperations and how they're implemented in hardware. When we think about computers, we often imagine software and applications. But at the very core, every calculation, every instruction is broken down into tiny steps called microoperations. Arithmetic microoperations in particular are the foundation. They power addition, subtraction, loops, counters, and even complex algorithms. In this session, we'll uncover how these microoperations are designed, how they're optimized in hardware, and why they're so critical to CPU performance. Let's begin with the basics. Micro-operations are the smallest atomic operations a CPU performs on the contents of registers. Without them, no instruction could ever be executed. There are four broad categories: arithmetic, logic, shift, and control. Today, we're focusing on arithmetic, the ones that deal directly with numbers. These are the building blocks for higher level operations like multiplication, division, and even addressing memory. Think of it as this way. When you write a simple program like C is equal to A plus B, that line is broken down into several micro operations inside the CPU. The magic happens because arithmetic micro operation translates software instructions into hardware level actions. This is a diagram which depicts the different types of micro operations like we've already discussed, which include arithmetic, logic, shift, and control micro operations. So, why do we why do we even care about these micro operations? First, they're fundamental to computation. Every arithmetic expression in any program is ultimately reduced to these tiny steps. For example, calculating C is equal to A plus B into D, as you can see here, involves a multiplication microoperation, followed by an addition microoperation. Secondly, CPU performance depends heavily on them. The speed of addition and subtraction directly impacts the processor's overall speed. That's why computer architects spend so much effort designing faster adders. And finally, they're used everywhere in counters, loops, iterations, stack operations, and address calculations as well. In short, arithmetic micro operations are like the alphabet of CPU's language. Now, let's look at the specific types of arithmetic micro operations. We have addition, A plus B, the most basic operation. From it, we derive many others like subtraction, A minus B, which is performed using complements, as we'll see later. Increment, A plus 1, and decrement, A minus 1, are used constantly in program counters, loops, and stacks. And finally, we have transfer, which moves data without changing it. These simple operations might look trivial, but together they are powerful. For example, multiplication is just repeated addition, and division is repeated subtraction. So the entire arithmetic world is built from these few micro operations. Let's zoom. Let's zoom into addition, the king of arithmetic operations. Addition is implemented with circuits called adders. The simplest is the half adder, which adds two bits and produces a sum and a carry. But in real processors, we need a full adder, which can handle three inputs, two bits and a carry from the previous stage. By chaining full adders, we create multi-bit adders. The most straightforward is a ripple carry adder. It works, but it's slow because each carry must ripple through all the bits. To fix this, engineers designed the carry look-ahead adder, which calculates carries in parallel. This dramatically speeds up addition, making it practical for modern CPUs. So, when we talk about clock speeds in gigahertz, remember, they depend heavily on how fast we can add numbers at the hardware level. Subtraction in hardware. Subtraction could be implemented directly, but that would mean building extra hardware. Instead, computer designers use a clever trick: two's complement representation. Instead of designing separate subtractor, we use the same adder circuit for subtraction. The idea is simple. To compute a plus b, we take the two's complement of b and add it to a. That means invert the bits of a, add 1, then feed it into the adder with a. For example, 7 minus 3 in binary is just 0, 1, 1, 1, plus the 2's complement of 3, which comes out to 0, 1, 0, 0, or 4. This saves hardware, simplifies design, and allows one unified circuit to perform both addition and subtraction. Now, increment and decrement. Increment means simply adding 1. It's used constantly in program counter, which fetches the next instruction. Decrement means subtracting 1, which is often used in stack operations when pushing or popping data. The beauty here is efficiency. Incrementers and decrementers are lightweight, fast circuits. They don't need full adders that are optimized for single bit changes. In most CPUs, increment and decrement happen in a single clock cycle. Without them, loops, stacks, and even instruction sequencing would break down. Now, let's talk about circuit design. It would be inefficient to build separate hardware for addition, subtraction, increment, and decrement. Instead, we use a unified arithmetic circuit. This circuit takes two inputs, A and B, and uses multiplexers to select the operation. A single adder performs the actual arithmetic and control lines decide whether to add, subtract, increment, or transfer. This design makes the hardware compact, efficient, and easier to control. It is a great example of engineering elegance, achieving more with less. At the, at the heart of every CPU is the ALU, the arithmetic logic unit. The ALU combines both arithmetic and logical operations in one integrated unit. It accepts inputs A and B, applies control signals, and produces outputs along with status strings like carry, zero, and overflow. When you hear people say the CPU executed an instruction, most of the time it means the ALU performed a microoperation. That's why we often call the ALU the mathematical brain of the computer. Without it, computation as we know it would not exist. Here's a simple example of how all this theory comes together. Imagine a 4-bit arithmetic circuit with two inputs, A and B, and control lines that let us choose between addition, subtraction, incrementation, decrementing, or even transferring. The output is simply another 4-bit number. Although this looks small, it scales. The same principle works for 8-bit, 16-bit, 32-bit, and even 64-bit processors. This is how micro-level design becomes the backbone of large-scale CPUs. By studying this, we get a peek into the building blocks of real-world processors. Arithmetic circuits also produce special conditions we must handle. Carry occurs in unsigned addition when the result exceeds the word size. For example, 1111 plus 1 in 4 bits produces a carry out. Overflow happens in signed arithmetic, where the result can be represented correctly. For example, 7 plus 5 in 4 bits signed gives 12, which can't fit the overflow, which can't fit and eventually results in overflow. Processors use status flags like CF, carry flag, or OF, overflow flag, to detect these. These flags are crucial because programs may branch based on them. For example, jumping to error handling if overflow occurs. So, while addition looks simple, handling these cases is vital for correctness. These are a few examples of what we just discussed and include examples of carry and overflow as well. So, where do we actually use these micro operations? Well, everywhere. The program counter increments with every instruction cycle. The stack pointer increments and decrements as we push or pop data. Loop counters rely on increment and decrement operations. Address calculation for arrays or pointers involves addition. Even evaluating expressions in high-level languages breaks down to these basic microoperations. In short, microoperations are the CPU's native language. Everything else, from AI to video games, is built on top of them. Of course, engineers are never satisfied with basic designs. To improve performance, CPUs use optimizations. Carry look-ahead adders reduce delay. Carry save adders speed up multiplication. Pipelining overlaps arithmetic steps to increase throughput. Dedicated multiplier or divider units accelerate heavy workloads. These optimizations are why modern CPUs can perform billions of operations per second. They show how much thought goes into making these simple micro operations as fast as possible. Let's summarize. Arithmetic micro operations are the foundation of computation. Addition, subtraction, incrementation, and decrement form the core. Subtraction is done with complements, saving hardware space. Unified circuits and the ALU combine arithmetic and logic for efficiency. Hardware optimizations ensure speed and scalability. In a sense, every program you write, no matter how complex, eventually boils down to these basic microoperations running at lightning speed inside your CPU. Thank you for listening. I hope this talk gave you a deeper appreciation for the elegance of computer architecture. The next time you run a program, remember, beneath all the complexity, it's these simple arithmetic micro operations quietly working at incredible speed to make everything possible.